Yo, Brian.
Yay! Hey Gerald, are you at the library still?
Yeah, yeah,
Oh
yeah,
dang,
yeah. I'm in
where?
one of the bathrooms.
Oh, which floor are you on?
It's like in the basement, but like you keep going.
Oh, you keep going down, like at the
Yeah, you
the
keep
restroom
going.
area, right?
It's where they have the microform, the like the digital scanners with
Oh
all the
shoot,
samples, assays. Yeah, yeah.
dang. Uh-huh.
You
Is
know,
that where
you
you
know,
like go to study? Usually you go to
yeah.
study spot.
I can hear the people talking outside in the tutoring. I can hear
Mm.
the noise. Like it's not that far away.
Yeah, I
That's
see, I
usually.
see.
I got one question, my man. So
Yeah.
I'm looking at. Okay, I'm on this. Here, let me show.
Oh, you could join the Zoom on your
Oh,
iPad as well, and then you could share your screen. I can make you
okay,
co-host and you
okay,
can share
okay.
your screen.
Okay. Um, Figure that out. Uh, are
Are
you?
there a lot of 118B people at the tutoring place right now, just like
Oh, I haven't
asking
checked yet.
questions? Oh, I see, I
I've been
see.
here for like 2 hours.
Yeah, they just had their final.
Oh yeah, yeah, 18B.
Yeah.
Yeah, I heard at six, right?
Yeah, 6 to 8.
Hmm. If I were them, I would have just went home.
Yeah, same.
Yeah. Do you expect a lot of people to show up here?
Um, and office hours post final or
Hmm.
post midterm, not a lot of people showed up. But when I
Oh,
held the review session, it's like 50 people showed up.
oh, you're an actual TA?
No, this office hours is just like my own thing. Like I want to do like my
Oh,
own
okay. Okay, that's
yeah.
cool. That's
Uh-huh.
sick.
Yeah, yeah.
Okay, I'm downloading the Zoom on my iPad at the moment,
Mhm.
but can I just tell you the problem? It's like what's the strongest acid?
Oh yeah, you can tell
Yeah,
me the problem and I can share you my screen on my
okay.
iPad and then I
So
could try drawing it out.
I narrowed it down. It was a multiple choice. I narrowed it down to two answers. Uh,
Uh-huh.
so they're both benzenes. Here, I can just tell you.
Yeah.
Is that okay? Okay.
Yeah, yeah.
So they're two benzenes. They both have different substituents though. And I'll tell you
Mhm.
what they are. So they both have a carboxylic acid, like at the top right. Yeah, somewhere doesn't matter. And then one of them has a para ketone, a two carbon ketone, para to the carboxylic acid. Yeah, and then the other one has a meta halogen, and that's the one. So the answer is the left, but I have an absolute
Mm.
no idea why.
Right.
So
So
yeah,
what's your thought process on this? Like
okay,
how
yeah, yeah. Yeah.
would you think about this?
So I was thinking, the halogen, for example, is a withdrawing group, right?
Mm-hmm.
So
Right?
that would increase the acidity, if I'm not mistaken. So that was my reasoning.
Mm-hmm.
And it's in the meta position, so uh,
Mm-hmm. Right. So
yeah.
that's a good reasoning. Electron withdrawals would increase the acidity. This ketone here is also partially positive and it's also a withdrawing group, right? But
Mhm.
this is a stronger withdrawing group because it is withdrawn by resonance. It is withdrawing the benzene's electrons through resonance, whereas the halogen here is just withdrawing through induction.
Mm. Okay, and resonance is stronger.
Yep, resonance is stronger,
Mm.
where the resonance ones would actually put positive charges at the ortho and para positions relative to the EWG.
I
If
see.
we deprotonate the acid here, we know that the conjugate base is going to have a negative charge on that carboxylic acid there. This negative charge is most stabilized by the positive charge here because opposite charges attract, right?
Okay.
This halogen here puts negative charges, ortho and para to it, right? They are weak EWGs by induction only because the resonance overpowers induction. Yeah.
I see, I see.
Uh-huh.
Okay.
Right.
Um, so if there was okay, because they're both withdrawing groups,
Mm-hmm.
then you factor in the resonance and induction. That's when that
Yes.
if they were donor groups, then you could kind of what if they're both donor groups? Would
Right.
they
So mhm,
yeah.
it
Would
would
it
depend on the strength of the donor groups, right? Like let's say we have this carboxylic acid here compared to this carboxylic acid, and we have this donor group compared to this donor group here, right?
Mhm.
Which is a stronger donor group?
The I'm gonna say the ester.
The ether, right? The
The
ether.
ether, my bad, my bad.
Right. That ether there is going to donate electrons through resonance because it has a pair of electrons. And when we do all the resonance structures, we're going to see full negative charges on the ortho and para positions, right? Let's look at the conjugate base of this carboxylic acid here. Does this seem very stable? Negative charges next to each other?
Oh, not probably not.
Not
Break
as
it up,
stable,
right?
right?
Break it apart. So you want
Mhm.
positive charges.
Yeah, we want positive charges to stabilize
Gotcha.
the conjugate base. So this here is actually going to be the more acidic molecule here,
Mm,
right? Because that's not as destabilized as the one on the left, right? There will still be like negative charges on the ortho and para positions relative to the R group, but not as big as the ether group.
hmm.
Yeah.
Okay, that makes sense. Uh,
Hey Justin,
Hey, Brian.
how are you?
Oh, good. How are you?
Doing fine, doing fine. Oh yeah,
I
you wanted to go over that question for the like acidity based acidity thing?
yep.
Yeah.
Let's see if
Which
we can just pull it
exam
up.
was that? Again, I think I have it. Let me pull it
Oh,
up and
yeah.
share my screen. Yeah,
Let me check. I think it was either. Oh, it's exam B.
exam B. Okay, let me see.
Yeah. So spring 2023 final exam, section B.
Okay, okay. Practice final exam B. Okay, send copy, import. Here, import. Open. Okay, share screen. Okay, we have this exam, which this question here is asking for the amino acid that has the most strongly basic side chain.
Mm-hmm.
So let me copy and paste that problem and explain it here. Okay, so the R groups that we're gonna focus on are these R groups here, right?
Mm-hmm.
The next thing we're gonna do is look at the atom that is gonna be the base, right? And the base is gonna be the one with the pair of electrons that is the least stable. So for atom A, which one do you think is gonna be the basic atom? The one on the carbonyl oxygen or the one on the nitrogen?
The one on the nitrogen.
Right. So we said earlier that nitrogens are usually more basic than oxygen, right? Because nitrogen
Mm-hmm.
is less electronegative than oxygen. But we
Mm.
see that the pair of electrons on nitrogen here can do resonance with the carbonyl.
Okay.
Right. And if it can do resonance, it makes it more stable, less reactive. The pair of
Okay.
electrons on oxygen here can't do resonance because the oxygen there is already double bonded. So the pair of electrons there can't do resonance, making it less stable, more reactive. Right.
Okay.
So I'm gonna leave that pair of electrons open like that. Now let's look at this pair of electrons on this nitrogen versus this pair of electrons on that nitrogen. Which pair of electrons is more basic, less stable?
Okay. I'm assuming the one that's more basic would probably be the top nitrogen,
Hmm.
is my guess.
Right, that's correct. Because this top nitrogen here is already double bonded, meaning that that pair of electrons cannot do resonance.
Mm.
Whereas this pair of electrons down here is not double bonded, right? Like this nitrogen here is not double bonded at
Okay.
all. So it is participating within the resonance in the ring. Right. Now let's look at these pairs of electrons here. Which one would be the most basic pair of electrons?
Okay. I think the one that would be the most basic is probably the bottom one.
Right, the
Um.
bottom one, because that bottom nitrogen there is already double bonded,
Mm.
making the pair of electrons unable to do resonance. Whereas the other pairs of electrons, those nitrogens are not double bonded, where those pairs of electrons can do resonance with that double bond right there. Right. So let's get rid of this and this. The more stable the pair of electrons is by doing more resonance, the less reactive it is because it's so stable that it doesn't want to react, making it less basic. Right.
Okay.
And this oxygen here, that's the only one that that has a pair of electrons, so that's the most basic atom there. Right.
Wait, if it's less reactive, it's more basic?
Yeah, if it's less, wait, no, if it's less stable, it's more basic, right?
Okay.
Less stable, more reactive, more basic, right? Because if it's less stable, it's going to want to react with something to become stable.
Wait, so if it's more reactive, it's more basic? Sorry, I'm
Yeah,
a bit confused.
right.
Okay.
Less stable, more reactive, more basic.
Okay.
More stable, less reactive, less basic. Right? Basicity and reactivity are directly proportional to each other.
Mm.
Stability and reactivity is inversely related to each other.
Okay.
Right? The more stable something is, the less reactive it is. The less stable something is, the more reactive it is.
Okay.
So the next factor to look at is which atom is more basic, a more electronegative atom or a less electronegative atom, right? Which atom is more willing to give up electrons and attack a hydrogen?
So the one that's most likely to give up probably be the B, because that one has a free pair of electrons.
Right, so let's choose an atom, oxygen or nitrogen. Which atom is less electronegative, oxygen or nitrogen?
Nitrogen's less electronegative.
Yeah, nitrogen is less electronegative, meaning that the
Mm.
nitrogen is going to be more basic than oxygen's, right? Because nitrogen is more willing to give up electrons and attack a hydrogen, whereas oxygen, since it's more electronegative, it wants to keep
Mm.
its electrons. So let's get rid of
Okay.
the oxygen choices, right? Ignore that. And then we're going to
Mm.
look at the nitrogen choices, right? Since both of those nitrogens there have the same electronegativity and they both can't do resonance, the next thing we look at is which one will give us the more stable conjugate acid. So let's say that those nitrogens here get protonated, right? Like they grab a proton source from somewhere. What charge would that nitrogen have once it gets protonated?
Okay, once it gets pronated, it'll have a negative charge. Oh, sorry. I have a positive charge.
Positive charge, right. Positive charge. Um, positive charge here. Now,
Mm.
those are the conjugate acids that I just drew right there after it gets protonated. The one with
Mm.
the more stable conjugate acid is the one that came from the more basic R group.
Mm.
So we said earlier that this pair of electrons can do resonance like that, right? Do those
Mm.
arrows make sense? Right. That's going to stabilize that positive charge by making it neutral.
Okay.
Let's look at the other case here. This can do resonance there, stabilizing the positive charge like that. And the other side can also do resonance, stabilizing that positive charge even further, right?
Mm.
Which one of these is more stable, B or C? More stable conjugate acid.
C, because it can push the double bond, I'm assuming.
Right. Well, B can do that as well. It could push the double bond to the nitrogen, but we see that C can do that 2 times, whereas B can only do it once.
Mm.
Right.
Oh,
There's more
okay.
of it in C, like more resonance in C than in B.
Okay, so we can treat both, I guess, nitrogen groups kind of like electron donating groups as
Yes.
kind of how I'm saying
Nitrogens.
things.
Right. Those are considered
Okay.
electron donating groups.
Mm.
Donating electrons into this positively charged species, making it stable. Right. Where there's 2 EDGs on C, 1 EDG on B. Right. More
Okay.
stable conjugate acid. Means more basic group, right? And vice versa. More stable conjugate base, more acidic group.
Okay.
Mhm.
And just out of curiosity, what would happen if we reverse the question and say which amino acid is the most acidic?
Right. So if we were to reverse the question,
Mm.
let's say we copy that, paste this, and then erase that. When they ask for the most acidic group, the first thing I look at is the conjugate base, right? Because the more stable the conjugate base is,
Mm.
the more acidic the group is,
Okay.
right? And the conjugate base is the deprotonated version of the acid. So for A, the acid here is going to be the H from the amide right there, right?
Mm.
So let's say we deprotonated that amide and give that nitrogen a negative charge like that. That's the conjugate base of A,
Okay.
right? The base for B is going to be a negative charge on that nitrogen. Conjugate base of C is going to be a negative charge on this nitrogen.
Mhm.
Conjugate base of D is going to be the negative charge on that oxygen right there.
Okay.
Right. So once we have all the conjugate bases here, we got to see, let's say, the negative charge on A is on a nitrogen, negative charge on B is a nitrogen, negative charge on C is a nitrogen.
Mhm.
Right. So we see that A, B, and C can do resonance with the negative charge, like
Mhm.
that, right? D can't do resonance. Um, but let's look at the electronegativity factor. What will the negative charge be more stable on an oxygen or a nitrogen?
An oxygen.
An oxygen, right? Because oxygen is
Mhm.
more electronegative, right? Um, so I'm guessing it's gonna be A because when we do resonance for A, you know how the resonance structure of that will have a negative charge on that oxygen as well,
Yep.
right? Whereas the other ones, there's no oxygen here,
Mhm.
right? Um, Let me double check that really quick though. Right. Let me see. Okay, so when you take biochem, you're gonna know that this is asparagine
Mhm.
and this is serine here. Because I'm kind of in between the asparagine and serine right now, and I'm gonna see if one is more sick than the other. I'm making sure here. Right, pKa. Okay. Mm. So I'm getting different answers here. Some sources are saying serine is more acidic. Some sources are saying asparagine is more acidic. Let me see.
Okay.
pKa values of R groups on amino acids. And the one with the lower pKa will be the more acidic one. Let's see. This one. Asparagine. Yeah, I would say the answer is A if they're asked for the strongly acidic side chain, because this negative charge here is more stable than this negative charge on oxygen, since the
Okay.
negative charge on this here can do resonance. And the negative charge on this group is also on oxygen as well, but it's more delocalized than this group here. So I would choose A if it
Okay,
asks
and
for the
we'll
strongly
also
acidic.
prefer the negative charge on oxygen because it's more electronegative, I'm
Yep.
assuming.
More
Okay.
electronegative. Right. Where both A and D will have the negative charge on oxygen, but
Mhm.
because A can do resonance as well, A is more stable. The negative charge is more stable on A than on D.
Okay. Brian, I also have another question
Yeah.
on exam B. It's
hmm
problem number 9 for section B.
Yeah.
Because this one I found pretty interesting. I also chatted with another tutor about it a little bit.
hmm
But for this one, I noticed that there's another protecting group on the other amino acid on the carboxyl or on the C
Mm.
terminal end.
Yeah.
And what we're wondering is it even possible for the amine group to react with with the R group of another amino acid? Because for this one here, our R group has a carboxylic acid. So
Uh-huh.
I'm wondering if that's potentially the side product we can get.
Yeah, that's the other side product we could get, because
Okay, so that
DCC
can
here,
occur.
yeah, that can occur. It can occur. Right. Any carboxylic acid, it doesn't matter if it's from the R group or amino acid, or any amine. It doesn't have to come from a carboxylic acid. It doesn't have to come from an amino acid. Like any regular amine carboxylic acid with DCC would always create an amide, so that can occur.
Okay.
Yeah.
And can and if we have a side group that has an amine group,
Uh-huh.
is it possible for the carboxylic acid of another, or
hmm
the C end of another amino acid to react with that amine group?
Yes, it is possible too.
Okay.
hmm
All right. Thank you.
Yeah, no problem. It can be any carboxylic acid and amine group. It doesn't have to be the carboxy end or amino end of an amino acid. It could be from an
Mhm.
R group, or it doesn't have to come from an R group as well. If you just bring in some kind of random carboxylic acid like this, that would react with an amino group of an amino acid. If you bring in any random amine group like that, that would react with any carboxylic acid group as well. These could also react with each other in DCC as well to create this amide here.
Right.
Right?
So
It's
it
just
can be any carboxylic acid, any amide group, right?
right.
All right.
And it does have to be specific for amino acid or R group. It's just
Mhm.
any regular carboxylic acid or amine group.
Okay. Thank you, Brian.
Yeah, no problem, Justin. Hey, Gerald, did you have any other questions?
What's up, Brian? Are we able to go to the midterm or the midterm 3, like the one that he posts on the canvas, or what I need to share my screen?
This midterm right here that I have, or
It's not one of the. It's not the practice ones. It's the one that we actually took, and he posts them online. Like
oh
the,
yeah.
I think it's. Is it? No, it's not that one. It had like the one with the 9 multiple
Oh,
choice.
multiple choice. Yeah. I don't have that file, so
Oh,
could
okay.
you share your screen?
Let me
Your
see.
screen.
Let me see
Yeah.
what I can do.
Mhm.
Uh, Give me a moment. Hmm. Okay. All right. Are we there?
Yeah, I see it.
All right. So I'm looking at this one, number 7. Um, Answer is C. I don't. I see that the only difference between these two. Can you see my mouse?
Yeah, I can see your mouse. Yeah.
Okay. So the difference between these two is the opposing the axial directions of the extra carbon substituents. But I'm not really familiar with why it wouldn't be plausible to form them in the same direction rather than so I understand how you do this, but not this.
Oh, right. So
The other one's, of course.
when we
Mhm.
close a ring, right?
Mhm.
In this case here, let's look at this answer here, where he says that cannot be formed. We know that's a 5-membered ring, where if we want to make a 5-membered ring, I'm gonna number my carbonyl-carbon number 1.
Yeah.
I'm gonna go all the way down until my nucleophile is number 5. We cannot say this carbon is number 5 because that carbon there has no pairs of electrons to attack. So what we gotta say is number 5 is this oxygen on the left right here,
Okay.
right? When we close it, we gotta number it in a way that it goes all the way straight down. Since it's not going all the way straight down and it shifts to the left on the end, we gotta rotate these 3 groups here: the alcohol, the CH2OH, and the H. And
Can
we
I
gotta
ask?
rotate.
Can I ask why you skipped the first carbon?
Oh, right. I skipped the first carbon because I'm not numbering it in the official way where we number C1, C2, C3, C4, C5, C6. I'm just numbering it to help us close the ring,
Starting
right?
with the anomeric carbon.
Yes, I got the anomeric carbon. You could say A, B, C, D, E if you want. It doesn't have to be 1, 2, 3, 4, 5,
Oh,
right?
of course.
This is not the official way to number it. It's just to help me close the ring, where my number 1 atom is gonna be the anomeric carbon, which is the electrophile.
Mhm.
Right. My last numbering system is gonna be the nucleophile, which is number 5, oxygen, because the oxygen is the nucleophile.
Mhm.
Right. So we want the numbering system to go straight down. So to do that, I'm gonna rotate the alcohol group counterclockwise. This H2OH is gonna go counterclockwise as well to the H position. And then
Yeah.
this H position here is gonna go counterclockwise where the OH is. When I redraw everything, this is what I get.
Okay.
Where now the numbering system is going straight down. 1, 2, 3, 4, 5. Right? Where when we close the ring, this is gonna be 1, 2, 3, 4, 5, right there. Right? And do you know if the group is on the left side, would it go up or down in the ring? And if the group is on the right side, would it go up or
It'll go
down?
up. Left is
Yeah.
up, right is down, I believe.
Right, right, right. Let's look at carbon 4. Where is the CH2OH going to go? Up or down?
Carbon 4,
Uh-huh. The CH2OH. Where is the CH2OH at? The left side or the right side?
like on the new molecule you added.
Right. This is the same molecule, it's just rotated.
Oh, I see. Okay. So you want to have, if you're gonna form a new cyclic structure, you want to have it where the alcohol is on the bottom.
Yes, we want to where the alcohol is on the bottom. The attacking atom is on the bottom. That's what we want it to be like.
Okay, okay, okay. So the CH is on the right, so it's gonna be facing down. It's gonna be downwards, right?
Downwards, right? Where at C, the C2H on 4 is not down, it's up.
Okay.
So that's incorrect.
Okay, and then for the upwards part, like this is just to clarify why this is up and not down. It's because is it just because it's pointing up?
Oh no, that's not the case. If that CH2OH is going down, that would also be correct. That one right there, you know how you said it was the anomeric carbon?
Okay.
It could be the alpha or beta anomer. Right. Because when the oxygen attacks that anomeric carbon, right? What is the hybridization of this anomeric carbon here? Is it sp, sp2, or sp3?
The number one.
Yeah.
That's the sp3, sp2.
sp2, right. And you know how sp2s are flat and planar?
Yeah.
If it gets attacked, it get attacked on either the top or bottom side, giving you mixed products. The C2H could be top or bottom. The OH could be top or bottom. Doesn't matter.
Okay.
Right.
Okay. So it's impossible. Is there an instance where they can both be up?
For number 1,
So like if C would be correct, you would just have to rotate these in a different way. If
you
the
can't rotate it in a different way because for it to go up, right, you have to rotate it in a way where the C2H goes to the clockwise direction.
So
right?
so if the CH2OH started at the H, then essentially you can form the C product.
Yes.
Okay.
Yes.
Okay.
Yes.
All right. So I just gotta remember, alcohol needs to be placed down before you convert to the cyclic from Fischer.
Right. Right.
Okay, I understand that. And then these ones are pretty straightforward. So let me think about this. So based on the Fischer projection that you get, the fourth carbon where my mouse is always going to be a set location.
Yep, it's always gonna be set location.
Okay,
The
that
only
makes
one that
sense.
can change is the anomeric carbon,
Got
the
you.
one on the right.
I got you.
Hmm.
Okay, that was a really good explanation. Thank you.
Yeah, no problem, no problem. I'm glad it helped.
Okay, let me just take some notes.
Wait, is there if I ask a follow-up question on this problem?
Yeah.
So I'm wondering, how do we determine where the HOH2C group was on the left toward the left side of the oxygen for
Oh, on the
C?
new
Like,
structure that I
yeah.
rotated in? Right. So you know how I want to make a 5-membered ring and I start my number 1 atom at the anomeric carbon here, which is this anomeric carbon here.
Mm-hmm.
I want to go down to the 5th atom, which is going to be a nucleophile. So when I go down 1, 2, 3, 4, I can't say that that carbon there is 5 because that's not nucleophilic. That's not the one that
Mm-hmm.
will attack. The 5 is going to be either the oxygen or hydrogen, which is
Yep.
always going to be the oxygen because the oxygen has a pair of electrons to attack. So you notice how it shifted to the left when I numbered the oxygen number 5,
Mm-hmm.
right? But that's not good to close the ring. We gotta make sure the numbering system goes straight down or the alcohol is on the bottom, right? To make the alcohol on the bottom, in one step, where do you want to rotate the alcohol? Clockwise or counterclockwise?
We want to rotate it counterclockwise.
Counterclockwise, right? That's gonna rotate all of those 3 groups on that same carbon counterclockwise as well. Where you notice how the C2H is on the right side and the H is on the
Mm-hmm.
left side now?
Actually, I think I was referring more to like the top C H2OH group.
Oh, the top C2H. I see, I see, I see.
Yeah, that
Okay,
one.
okay, okay. Yeah, this top C2H group right here, that's part of the anomeric carbon. It's bonded to the anomeric carbon right there.
Mm-hmm.
Right? When that anomeric carbon gets attacked, does it have a preference where it attacks top or bottom, or is there no preference because it's flat and planar?
Mhm.
Hmm. I'm not sure. I think there is a preference because I'm
Oh,
I'm
right,
looking
right,
at
right. There is a
CMB.
preference because the beta anomer is more stable than the alpha anomer, but it could like attack either way, top or bottom, right?
Okay.
Where when it attacks top or bottom, you know how the carbonyl oxygen is gonna be the alcohol on carbon 1,
Mm-hmm.
right? The anomeric carbon is also attached to a CH2OH, where depending on where the alcohol goes, if it goes up, the CH2OH is going to go down. If the OH is going to go down, the CH2OH is going to go up. Right? So it's randomized because we attack a randomized sp2 flat planar carbonyl
Mm-hmm.
carbon. Right.
So that group can be facing up or down. So does it
Yep.
mean it could be C or D for the answer? Or actually, that's just what I'm wondering.
So for
In terms of the,
D, it's not going to be the answer because the answer is what would not be formed. D could be formed.
oh, okay.
Right, because C2OH on number 4 is on the right side, which we see on the number 4 for D, the C2OH is down, right? C or D, this is correct. This is good. That could form, right? But for C, this cannot form because the C2OH is up, which is not good because C2OH here is on the right side, which means it has to go down, right? But this one is bad because that's up. This is good for D because C2H is down.
Okay. Sorry, I'm still a bit lost. So why would it be C again? Why is it up being an issue? Does it have
It's
to
an
be on the
issue.
opposite side?
Right, because do you remember if we topple the vertical line like that, where would the group go if the group is on the left side of the Fisher projection? Like where would the groups go if they are on the left side of the Fisher projection here?
If you're on the left side, they would be, I believe, down.
Oh, they would be up because
Oh,
think about the Fisher projection like my arm like that. I'm gonna
mhm.
rotate it clockwise like that, and when I do that, this is what I get here. Right, the CH2OH, and then down 1, 2, 3, 4. This is gonna be 1, 2, 3, 4, 5. Right. When I rotate my arm clockwise, let's look at carbon 2. You know how the hydrogen is on the left side? I'm gonna say the
Mhm.
hydrogen is on the left side right here, which is the pencil. If I flip it like that, we see the hydrogen is going up.
Okay.
Right. So everything on the left side is gonna go up. And then let's look at carbon 2 again. Let's say the alcohol is on the right side, which is on the right side. If I flip my arm clockwise, then the alcohol is gonna go down. So everything on the right side
Okay.
is gonna go down. Right. So at carbon 2, H is gonna go up, OH is gonna go down. Carbon 3, where's the OH gonna go? Up or down?
Um, the OH group's gonna go down.
Right, so for carbon 3, the OH group, is it on the left side or right side?
That's on the right side.
Right. So, wait, this is the carbon I'm referring to right here, like carbon 3, right?
Hmm.
This alcohol here
Okay.
is on the left side.
Okay, so wait, no, that'll be up because it's on the left
Yeah.
side. Okay.
Right, right. How about carbon 4? Where would CH2OH go?
CH2OH would go down.
Yep, because it's on the left or right side?
Right side.
Right side, right. So everything on the right side here is going to go down. Everything on the left side is going to go up. Let's look at C. The answer C here.
Hmm.
Is this CH2OH going up or down?
So that CH is going up.
Yep, it's going up. Does that match with what we said earlier?
It does not.
It does
Oh,
not.
okay.
Yeah. Right.
Again, how come the molecules A and B can form?
Yeah, so that's a six-membered ring where the numbering system here is going to be different, right? For A and B, we have to number it in a different way.
Hmm.
So I'm going to redraw this Fisher projection like this. Right? Where the CH2OH, I just expanded it out into this CH2OH right here. That's the exact same thing. Right?
Okay.
Does that make sense so far?
Yep.
So when I close the ring, I'm going to start my number 1 atom at the anomeric carbon, the one that gets attacked right there. If I want to make a six-membered ring, I want to go down all the way to the sixth atom, which is going to be a nucleophile. 1, 2, 3, 4, 5, 6, right there. Where you know how the alcohol we want at the very bottom, it's already at the
Hmm.
very bottom, so we don't have to rotate anything.
Yeah.
Right. So when we make a six-membered ring, this is the atoms for the six-membered ring. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right. So let's look at carbon 2. Where would the alcohol go? Up or down? At carbon 2.
So for carbon 2, the alcohol would go, I believe it would be down.
Down, right? Because it's on the right side.
Hmm.
So that checks out for A and B. How about carbon 3? Where would the alcohol go? Up or down?
The alcohol would go up.
Yeah, because it's on the left side, which checks out for both A and B. How about for carbon 4?
Would be up.
Yeah, because it's on the left side. So it's going to go up, which checks out for A and B.
Okay.
And then for carbon 5, there's two H's there. The two H's there is going to be up and down because, yeah, it's just two H's there, right? But the anomeric carbon, you know how we said it's flat, sp2, and planar? And when it gets
Mhm.
attacked, it could get attacked on either top or the bottom side. That's why at the anomeric carbon, number 1, the alcohol and CH2OH can be flipped,
Okay.
right? One is the alpha anomer, one is the beta anomer.
Okay.
Right.
All right. Thank you.
Yeah, no problem.
Yo, Brian,
Yeah.
I just got a brief question about Merrifield synthesis. So I understand that's not a topic that was explicitly stated that we needed to know, but like, are the reactions in the synthesis relevant to the course, or is it just kind of a overview of, like, the Merrifield is like a general application in like actual science? Is that like something that we would probably need to know during the for the exam?
Is that for amino acids or
For
heterocycles
amino
or what?
acid.
Amino
It was like one
acids.
of the, yeah,
Merrifield synthesis.
it's like an 8-step process or something like that.
Oh shoot, let's see.
1, 2, 3, 4, 5, 6, actually.
I wouldn't worry about that. No, I wouldn't worry about
Okay.
that for this final.
Not even like a conceptual, like I know they like they take off they basically let me see exactly what happens in this. Yeah, they basically just
They use
add
DCC.
they use DCC, yeah, and then they use
Yeah.
hydrofluoric acid at the end.
Right. So I think the most important thing is to know the DCC coupling between the carboxylic acid and amino group to make the amide or peptide bond between two amino acids, and why we have to use protecting groups to get a certain specific peptide we want, right? Because if we don't protect the amino and carboxylic acid group, then we get a mix of products of undesired mixture. So that's
So
the
like,
most important thing for explanation, right? The bare fruit thing is just a specific thing that it's like too specific for the class. The more general idea is the application is the one that's going to be tested on.
I understand.
Right.
So I want a brief overview on the amino acid synthesis. I'm not too familiar with them, but what kind of groups would you like be aware of that would attack the nitrogens, and then another one that would attack the carboxylic acids that we need to, that's why we need the protecting groups for. Like, what kind of reagents are we looking for?
That would protect the amino group and
Or
protect
that like yeah, like in general, I know you have the Bach, whatever that is, Bach
Bach, right?
Bach 2O, I think.
Yeah, Bach 2O, Bach 2O,
Bach
right?
2O, and then you have CBZ.
CBZ, right? Those two right there will protect the amino group of the amino acid. There's one that would protect the carboxylic acid end, which requires two steps. The first step is a base like K2CO3 that would deprotonate that carboxylic acid into the carboxylate. And then the second step is to use a CH3I to create an ester, right? And then that ester is no longer a carboxylic acid. It would not do DCC coupling because DCC coupling requires a carboxylic acid and an amine group. If we create that ester right there, that is protected.
The first step was what?
The first step was a base to deprotonate the carboxylic acid, which is K2CO3. That's a type of base that can deprotonate the carboxylic acid. Right, K2CO3.
Okay.
Yeah.
Okay, I think for the purpose of the class, he combined them both. He was just like, use K2CO3 and the
CH3I, yeah. They go together. They're two steps, separate steps. Right.
I get it. It's just one step in the class for us. And then
one step, I see.
Yeah. It's just all together. And then to take it off is NaOH water.
Yeah, to take it off NaOH water. Actually, yeah, they could actually be together because K2CO3 would not interact with the CH3I. The K2CO3 would interact with the carboxylic acid, and then the carboxylic acid would react with the CH3I. So yeah, that's all together.
I could be any kind of halogen.
Oh yeah, it could be bromine, chlorine, not fluorine.
Not fluorine. Okay.
Yeah.
And then for like a synthesis, for example, if you wanted to introduce a Bach 2O, is that just enough to just write out? Just say Bach 2O, or do you?
Yeah, for synthesis, Bach 2O. Yeah. Right. And then you just gotta write Bach NH or something like that on the amino acid. Right.
Oh yeah.
And then to deprotect the Bach, do you remember the reagents to get rid of the Bach?
It's H2SO4 and water.
Yeah. How about the CBZ?
CBZ is it's the different one. I think it's H2.
Yeah, H2 PDC.
PDC. Okay.
Yeah. Right.
PDC.
Nice.
Okay. All right. Well, let me see if I can find another question on the final.
I've got a question for the final, if that's all right.
Yeah.
So this one was on the practice final, section A, and it was number. Let me see, which one was it again? Yeah, it was number 8 for synthesis.
Okay, number 8 for synthesis. Let's see.
For this one, they did a really weird step. I looked at the solution earlier, and they did some sort of Gabriel synthesis, and I don't know exactly how they used it.
Let me see. Okay, import, share screen. Okay, number 8. Oh, this one.
Yep, 8A specifically.
8A specifically.
Wait, was that? Hold on. Is that the right one? Is this for spring 2023, section A, helix?
Oh, this.
8A.
Wait. Hold on. Oh, wait. No, this is. This one.
Okay, yeah, that's the one.
I see. Oh, okay. So when you see this molecule here, it's very bulky and big, right?
Mhm.
Let's first identify what functional group this is right here. What are the two functional groups you see in this product here?
This one, it looks like I see some sort of large, I guess, R group and maybe like an amine.
An amine is one. What is another functional group you see?
Um,
Carbonyl.
Carbonyl,
Yeah.
right? Which is a carbon double bond oxygen, right?
mhm.
So let's look at the carbonyl carbon. What is this carbon called in relation to the carbonyl? Like, what is that carbon called? The position of that carbon relative to the carbonyl?
The alpha.
Alpha carbon,
Okay.
right? One carbon away from the carbonyl is the alpha carbon. What's one away from the alpha carbon? Two away from the carbonyl.
Beta carbon.
Beta carbon, right? And you notice how at the beta carbon there's an amino group attached to it at the beta
Yeah.
carbon.
Mhm.
This is called a beta amino carbonyl. Whenever you have a beta amino carbonyl, what reaction do you guys know that could make this
Is it
beta
mannich?
amino mannich reaction?
That's her
Yeah, mannich reaction.
favorite one.
Yeah, that's your favorite one?
For sure, yeah.
Oh, that's a big bulky one.
Yeah.
Right. So for mannich reaction, there are three reagents that are needed to make this occur, right? What? Wait, but there's two things: the nucleophile and the electrophile. What is the nucleophile of a mannich reaction?
Is the amino? Yep.
Right. So the nucleophile is going to be an enol, and then the electrophile is going to be an iminium
Okay, okay.
ion, right? But the iminium ion is composed of two things. The amine group is one of them, and the other one is a more reactive carbonyl. An
Mm.
enol is going to come from the less reactive carbonyl, right? So here's how to go backwards retrosynthetically if you have a beta aminocarbonyl, right? The alpha carbon that you labeled is always going to be the alpha carbon of the enol. The beta carbon is always going to be your carbonyl carbon of the more reactive carbonyl, most likely an aldehyde or formaldehyde,
Mhm.
Mhm.
right? Because carbonyl reactivity goes something like this. Right, where at this left side here, we have formaldehyde. In the middle, we have just a regular aldehyde. And then at the right side, we have a ketone, right? Do you guys know why this formaldehyde is the most reactive compared to these ones here, and why ketone is the least reactive? 118B concept here.
Because the charge stays on the oxygen.
The charge, like oxygen would withdraw electrons
Yeah.
from the carbon right there, giving that carbon positive charge, right? All of them have
Oh,
oxygens on them. But what's making the positive charge on the ketone smaller?
it's got two R groups, so it
Yeah,
can
and what
have
are
a
our groups?
positive carbocation.
Right, and our groups are EDGs. They are stabilizing that carbocation
Mm,
there, right? The ketone has two R groups stabilizing it. The aldehyde only has one R group stabilizing it. Formaldehyde has no R groups at all. No R group stabilizing the positive charge, which is why formaldehyde has the biggest positive charge
Mm-hmm.
and the most reactive out of all the aldehyde and ketone. Okay, so this is what cut I make to predict the reactants here. I always make a cut between the alpha and beta carbon right there, where the alpha carbon is going to be the carbon of the enol. And the enol is going to come from this less reactive carbonyl here, right? Where the alpha carbon is this alpha carbon right here. This is a less reactive carbonyl because you notice how that's a ketone with two R groups. One R group is a methyl, the other R group is a phenyl group.
Mm-hmm.
Right. That's the enol from the less reactive carbonyl. Then I make a cut between the beta carbon and the amino group, which is that cut right there, where we said the beta carbon was the carbonyl. So that blue dot I made right there is this blue dot right here. And what's a carbonyl group? Like what is a general structure of a carbonyl group? What two atoms are composed of a carbonyl group?
Just hydrogens.
Carbonyl is a carbon double bonded to a
Oh, okay. Oxygen?
oxygen, right? So that carbon there came from that carbonyl right there, right? There was an oxygen there somewhere, like double bond
Hmm.
oxygen there somewhere, right? What is attached to the beta carbon right now, as you see in the products? Like ignoring the cuts I made, what atoms is attached to that beta carbon? What two atoms?
Carbon,
Um,
hydrogen.
hydrogens, two hydrogens, right? Two
Oh, okay.
invisible hydrogens, right? Let's draw those two invisible hydrogens out explicitly like this. What did I just draw out here? What is that functional group called?
It's formaldehyde?
Ooh,
Formaldehyde, right? Which is more or less reactive than this ketone that I drew out earlier.
More.
More reactive, right? So that is the one that is gonna be part of the iminium ion that forms, right?
Okay.
And this amine group that I drew here is gonna be this amine group right here, NH2, right?
Mhm.
You notice how this R group of the amine group looks very similar to that R group on the study material we have, right? How can we replace that bromine with a NH2 group, 118A reaction here?
I'm not really sure.
Right, it's gonna be NH3 ammonia, right? Where the NH3 nitrogen with the pair electrons is gonna attack that carbon, kick out the bromine, SN2 reaction.
Oh,
hmm.
okay. So you get an NH2, okay. But don't we need a negative charge on the aminium? The amine group?
A positive on the iminium group, right? We do, but the iminium group is formed between the amine group, which we just created at step 1 here with SN2. That's the amine group here. It's gonna react with this carbonyl here to create the iminium.
Okay.
Right, the more reactive carbonyl, because the iminium is not just from the amine, it's from the amine plus the more reactive carbonyl, which is this formaldehyde right here. Right. Once we have that, it's gonna form this iminium here. You don't have to draw this. You could just like include this and the more and less
So,
reactive carbonyl right away together all in one step. But I'm gonna draw in the intermediate here with the iminium ion,
so
right?
what reactants did we use to create the aminium ion again?
Um, amine and the more reactive carbonyl plus some kind of acid catalyst, right? The amine is here. The more
Hmm.
reactive carbonyl is here, like we said earlier. And let's put that under HCl. That's gonna create this iminium here, where the nitrogen has a positive charge there, right? That's the iminium there,
Okay.
Okay.
right? And then we said that the mannich reaction is reacting with an iminium ion, which is the electrophile, and the nucleophile was an enol, where the enol is just gonna come from this group here that I drew out earlier when I made the cut between the alpha and beta carbon, right?
So do we only
With
need NH3 for that reaction to the NH2?
yes, we need NH3 to convert the bromine into the NH2.
Okay, and that's all that you need?
And you might need a base like K2CO3 because it will go through
Okay.
this NH3 plus.
Okay,
To
I get
deprotonate that NH3 plus, we use a base like K2CO3 to deprotonate that NH3 plus to NH2
so
neutral.
something like NaOH won't work?
NaOH, that's more dangerous because it could deprotonate an alpha hydrogen
Okay. Okay.
here, which can
So you want a weaker
do
one?
something else. Yeah, we want a weaker one here.
Okay.
Yeah. Right. But if you put NaOH, I think that they'll still give you credit for it.
Okay.
Okay.
So
So just to confirm, so it's only the NH3 that created the amide group, right?
Yes, right. SN2 reaction.
Okay, and then it was reacting with the acid and the was it formaldehyde?
To create the
Okay, to create the amide I guess our
iminium.
aminium electrophile.
Right,
Okay.
electrophile. And then this two reagents here will make the enol, which the enol reacting with the iminium creates the mannich beta aminocarbonyl. Right, where the star atom is the alpha atom, the dot atom is the beta atom, which is this beta here, right? But then when we make that cut between the beta atom and the amine, that's where the amine group came from here. Yeah. Right, like the beta carbon here is the
So wait, how did we add the beta carbon?
so alpha beta nitrogen.
Hmm.
Something is
Mhm.
Wait, let me double check this really quick. Yeah, I guess that. Guess that. I see, I see, I see. So this iminium ion I drew here, right, is wrong because the beta carbon, right, is this beta carbon right here, where to get the iminium ion correctly, look at the carbonyl-carbon of the more reactive carbonyl, which is this form aldehyde right here. Draw
Hmm.
that out like that. You know how those two are bonded to the hydrogens like that, which are those two hydrogens right there? Substitute the oxygen with the nitrogen of the amine group, and then still draw that R group of the amine group out like this. And then get rid of one hydrogen, which gives that nitrogen one hydrogen and 4 bonds still, so positive charge like that. So this is the actual iminium ion here. I drew out the iminium ion incorrectly previously. This is the correct iminium ion here. Right? Where this is the beta carbon that was on the beta aminocarbonyl. When we made that split between the beta carbon and amino group, this portion here now makes sense. Now makes sense where that was the
Okay.
amine group right there, right? And then this portion here at the bottom is the formaldehyde portion right there, right? The way I drew the iminium ion earlier was wrong. This is the correct iminium structure here that gets formed between this amine and this aldehyde here, right? And then when this iminium ion gets reacted with this eno here, it would form this here now, right? Because this alpha carbon of the ketone here would react with the iminium carbon there, which is the dot carbon. So that's the new bond between the alpha and dot carbon right there, the star and dot carbon right there, which is the carbon of the formaldehyde, and then the amine group is right there, which is this part right here. Right. Does that make sense? Oh, I think you're muted, Gerald.
Yeah, I saw that. So, at the end, we would have water produced as well,
At the end, we would have, let's see.
right?
Yes,
Because you
water would be
take,
produced because that carbonyl right there, when we do the whole iminium process, that oxygen
Mhm.
leaves out as water.
Okay, but also, so it takes a hydrogen from each of from the amine and from the weaker carbonyl, right?
Yes, 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 yes.
Okay,
It gets those two hydrogens out, and then the oxygen that it comes from it is that
those
carbonyl oxygen.
okay. And the hydrogens from the reactive carbonyl stay within the molecule.
Yes,
Okay,
stay
got
with
you.
the
They
molecule.
stay on the
Right.
C. Okay,
Yeah, stays on the C.
got you.
Okay.
Okay. Uh-huh.
Let's have a quick question. So for the mechanism, when we join our amide electrophile to the
Oh, iminium.
aminium to the
Right.
carbonyl, so what would be the electron movement for that? Will we just, I guess, push
Mm.
electrons toward the nitrogen
Right.
from
So
the carbonyl?
when we form the enol from that lower reactive carbonyl, this is what
Hmm.
it would look like. Where this is the enol here, like once we tautomerize it into the enol with the acid,
Oh, okay.
this alcohol will reform its carbonyl and use this star atom here to attack that dot atom and pop that double bond onto the nitrogen right there, right? Where you know how when we do that, we make a new bond between the star and dot atom. That's this new bond between the star and dot atom right here. And when we pop the double bond onto the nitrogen, that neutralizes this nitrogen here, which is this neutral amine group here.
Okay, and how did we create that type of nucleophile?
Yeah, we created this type of nucleophile through tautomization in acidic conditions, from a carbonyl to an enol, tautomization.
Okay, so I'm assuming we deprotonated I guess the methyl group and then
Right, so
protonated
this
the
is in
oxygen.
acidic conditions. So this is tautomization in acidic conditions, not basic conditions. In
Oh.
basic conditions, it would deprotonate the alpha hydrogen.
Mhm.
Right, but since this is in acidic conditions, what happens first is we protonate the carbonyl oxygen, and
Mm.
then the alpha carbon gets deprotonated by the conjugate base to form that enol, neutral enol.
Okay, thank you.
Yeah, no problem. Okay, any other last minute questions?
I think I can maybe think of one last one. Hoping this one will be quick. It was on a predicted product for problem H of
For the
this
same,
exam. Yeah, for the same one.
yes, this one.
Yes.
So when you see an aldehyde at the reactant, reacting with these three specific reactions, right? An amine, excess NaCN, HCl, and then H2SO4, H2O heat, right? This is strecker synthesis of amino acid. The first reaction here would create an iminium ion. The second step would make a cyanoamino group. And then the third step would do hydrolysis of the nitrile to carboxylic acid. So the first step would create this structure here. Right? It would be neutral, but you know how in the second step we have HCl? That HCl would protonate that neutral imine to iminium, like that. Does that make sense so far?
Yes, I believe so.
Right.
Yep.
Because the carbonyl and amine reacting together makes an imine. Primary or ammonia amine. This is 1,9B reaction, the first step. And then the next thing for the second step is the Cn minus would attack this iminium ion, pop the ones to oxygen to get this. This is a hydrogen still, NH2, and then this is Cn here. Then the third step here, since we have a nitrile, which is a derivative of a carboxylic acid, that would get hydrolyzed with H2SO4, water, and heat to give you this carboxylic acid here, where the C of the nitrile is the C of the carboxylic acid, and we said the NH2 there. We see the NCC backbone of the amino acid there, where this is the R group of the alpha carbon of the amino acid. So we just created an amino acid through strecker synthesis. This is the specific set of reactions for strecker synthesis here. First, create the iminium ion. Second, create this cyanoamino group where there's a cyanide or a nitrile next to an amino group. And then the third step is to hydrolyze that nitrile into the carboxylic acid to get the amino acid.
Okay.
Yeah, strecker synthesis. That's the overall name. Strecker synthesis. The two other ways to create amino acids are modified HVZ, Helvor-Zielinski reaction, and Gabriel synthesis.
Okay, and just out of curiosity, what does the hydrolysis mechanism look like for the cyano group?
It's a long mechanism, right? There's a lot of proton transfer steps.
Okay, so we don't need to know it.
You do need to know it because it was tested on the midterm 1, and it could show up on the final again, where it would first go through the amide, and then that amide gets hydrolyzed into the carboxylic acid, right? I will look at the mechanism and explain to yourself each arrow what happens for each arrow.
Okay, thank you, Brian.
Yeah, no problem, Justin. Good luck on the final. Yeah, good luck on the final. Yeah.
Thank you, Brian. I got one small question. So what makes something a reducing and a non-reducing sugar?
Yeah, so a reducing sugar would be a hemiacetal on the anomeric carbon, right? Do you know what a hemiacetal is? Like, what is the carbon attached to?
Does that involve an ether?
An ether, OR, and then OH, alcohol, right? Hemiacetal has half OR, half OH. an acetal has two OR groups, right?
Yeah.
And then at the anomeric carbon, if there's an alcohol there, then that's a reducing sugar. At the anomeric carbon, if there's no alcohol group there, then that's non-reducing sugar.
Okay, that makes sense.
Yeah.
So
Right.
acetal would be a carbonyl, for example.
An acetal, we want two ethers, two OR groups on that anomeric carbon. So it doesn't have to, it can't be a carbonyl. It has to be two OR groups, right? So an example would be like this.
Okay.
Yeah, some other thing, right? Where this anomeric carbon here has an OR. That's a
Mm,
non-reducing sugar.
that makes sense.
A reducing sugar would be something like this, where we have OH, OR. That's a reducing sugar.
So, oh wow, okay. Okay. And it has to be anomeric.
It has to be the anomeric carbon, right?
Yeah, for sure.
Yeah. Every other carbon, you can't say. You have to focus on the anomeric carbon.
Okay.
Yeah.
All right, that's all I got for you.
Yeah. Okay. Good luck,
So much,
guys.
Brian. You're awesome.
Thanks, Brian.
Yeah.
Have a good night.
Yep, you too,
All right,
guys.
good night.
Good night.